In this section, we're going to stick to talking about reactions of aromatic rings, but we're actually going to be talking about the polar opposite of electrophilic aromatic substitution. Instead, we're going to be talking about nucleophilic aromatic substitution. So let's first just quickly review what happens in electrophilic aromatic substitution. The first thing is that your reagent is an electrophile. So in the nitration here, our reagent is basically NO2 plus, which is an electrophile. Then the aromatic ring acts as a nucleophile. And for one of the products here, we get the ortho-nitro group, and then we would also get the para. But the point of this is that the ring acts as a nucleophile, the reagent acts as an electrophile. In nucleophilic aromatic substitution, which is often abbreviated by this term SNAR, which stands for Substitution Nucleophilic Aromatic. This involves an aromatic ring with a leaving group, typically a halogen, and a nucleophilic reagent. So now what's going to happen, let's look at our first example where we have sodium amide, NaNH2. So essentially our reagent, if we break this up into Na plus and NH2 minus, our reagent is NH2 minus, which is an amide ion. This is now a nucleophile. So our reagent switches from an electrophile to a nucleophile. Now the aromatic ring acts as the electrophile. And the nucleophile ends up adding to that. Now the net result is similar in that we're adding something new to the ring. But what's going to happen is the halogen will act as a leaving group, and the nucleophile, NH2 minus, will replace it. Now what we find is that in many cases, these reactions are enhanced by having electron withdrawing groups on the ring. Why? That makes the ring more electrophilic. So again, we're seeing the opposite trend of electrophilic aromatic substitution. With EAS, electron donating groups increase the rate. With SNAR, electron withdrawing groups increase the rate. So in the second example, again we're using NaNH2. Cl is the leaving group, so the NH2 will replace it, and the product will be very similar to our first structure. We have the NH2 up here, but we still have the nitro group on the ring. So we're going to explore a couple of different mechanisms for nucleophilic aromatic substitution.